Hey everybody, and welcome back to Calc 3 Online. So today we're going to talk about two things associated with vector-valued functions, and one of them is arc length, and the other is curvature. And these are basically like properties of vector-valued functions. And it's kind of like when you study concavity for functions in Calc BC. Basically, it's like studying a property of vector-valued functions. And the for arc length, it's kind of actually important to like go back to what we're even doing when we like calculate arc length with in Calc BC. So the idea is basically we really are doing a super small like triangle problem is the idea. So if you have some sort of curve, you could draw like a secant line that connects just 2 points, like, you know, x sub 0, y sub 0, x sub 1, y sub 1. And there'd be some change in x in this triangle here and some change in y. And so to approximate this arc length here, like S1, we basically are taking that green hypotenuse of this triangle here. And the smaller we make these little delta x1s or delta y1s, then it gets to be a better and better approximation. And so really it all comes out of distance formula, actually. So you have the distance formula for, like, let's say S1 here is equal to the square root of x1 minus x sub 0 squared, and then plus y1 minus y sub 0 squared. And the idea is, like, we can think of this as delta, like, x1 squared plus delta y1 squared. And if you do, like, some clever kind of algebra, you can basically write this. I'm going to kind of go down here, actually, because I did not give myself enough room. But you can write this as delta x 1 squared times 1 plus delta y1 squared over delta x1 squared. So, you know, if you multiply that in, basically you would get the same thing. And then you can take the kind of square root of the delta x1 squared, and you get 1 plus delta y1 over delta x1 squared, and then a delta x1, and it's not squared. And this thing is kind of should look familiar, because this is like the dy dx squared, and then this is like the dx. And in Calc BC, you learn basically that is, you know, the integral of the square root of 1 plus the derivative squared dx is one way to just calculate like the arc length between, you know, 2 points like A and B or something like that. And really the idea is, like, if you think of the definition of an integral, it's a summation. And so to get a better and better approximation of this, you just take a sum of infinitely small little delta x, delta y's. And when you take something and you do like a sum over like super small amount of things, like I equals like 1 to n, and you basically take the limit as n goes to infinity here, meaning you're just splitting this up into infinitely small little like hypotenuses of this triangle. If you do this, this truly, by definition of what an integral is, it really would give you that integral from like a to b, and then the square root of like 1 plus f prime squared dx, which is your, you know, Calc BC arc length. And that's really what we're doing. I don't know if Mr. Mikau explained that last year, but that is the idea. And we're actually going to kind of use that idea to understand how to do it for vector valued functions. So we work in this course with like vectors, and so really we're going to work with the parametric arc length, and the parametric arc length is the one where you still have an integral, and it still goes a to b, and you still got a square root, but this time you got like dx dt, and then squared plus dy dt squared, and then you got a dt out here. So that's what you should have worked with last year in Calc PC. And the idea here is basically you're sort of just splitting the curve up into little line segments, and dx dt and dy dt is basically like doing, dx dt would measure like a change in x between, let's just say that's delta x. So that's like a change in x, like dx dt, with respect to a change in time. And then you got like a some sort of change in y per change in time. And you're basically just doing like a distance formula again. And you really just, when you take the integral, you're thinking of taking an infinite sum of like super small little line segments like this. So your dt's are super, super minuscule. And if you do super small little chunks like that, then you would actually truly approximate the length of this curve. And the one for 3D is pretty analogous, probably what you would think. You still have a lot of this, and you still have a dx dt squared. You still have a dy dt squared, but then you also have like a dz dt squared. And really it's just like hard to draw, but technically there is, some change in y, some change in x, and some change in like z between any two of these points, right? And so this really just measures that change. And when you, again, integrate between a and b, you would get an infinitesimally small change, and so you would get the arc length. And there's actually a way to write this a little nicer if you think of what the magnitude of r prime would be. So r prime is basically dx dt, dy dt, dz dt if it's like 3D. You could also have like 4D or 5D or whatever, but so then if you do the magnitude of r prime, right, the magnitude of r prime would actually equal this part right here. You would really just have the square root of all those squared, and that's how you find the magnitude of that vector, right? So this whole messy looking thing actually can be written as the integral from a to b, the magnitude of r prime of t dt. And that is actually how we typically see it in like really every math class from here on out. So the power of this is that, well, one, we don't have to write all these symbols, but also this works for any dimension. So we can have, 3D, we could have 2D, we could have like 8D, whatever we want, and we just basically tack on more terms like this. We just add another d variable dt squared and whatever. But that's basically how you'll see it. That is arc length for a vector valued function. So I just want to do an example. So it's pretty straightforward. You need to find r prime, and then you need to find the magnitude of it. And but let's just go through this example. So we've got r prime, we got r prime equals for this minus sine t cosine t, and then the integral of natural log cos t would be, you'd have to do like a chain rule, and so you would get minus sine t times or over cos t. All right, and then the magnitude of r prime would be the square root of sine squared. I'm just dropping the negative because it's squared anyways, plus cosine squared, and then really, again, you can drop the negative. This is really tangent, right? So I'm just going to say plus tangent squared. All right, and then we have, this is like that super famous trig identity, sine squared plus cosine squared, which is 1. So we have 1 plus tangent squared t. And this is another famous trig identity, 1 plus tangent squared is secant squared. So we have the square root of secant squared. And then we could write just secant. And so that whole big messy problem just boils down to really just doing the integral from 0 to pi over 4 of secant t dt. And this integral, probably one that you don't know just off the top of your head. It's kind of a weird one. It's in like the table of integrals in like the back of the book, or maybe it's the front of the book. I think it's the back. But so yeah, it's like a weird one where you go, just copying. If you look it up in the table, it is just natural log of secant t plus tangent t, and then we're like the absolute value of that, and then we're going to evaluate from 0 to pi over 4. If you've never seen y, I'm not going to go through it a ton right now, but I'll kind of give you the idea. Basically, if you do the integral of like secant x dx, you do this trick where you do secant x, and then you just write secant x plus tangent x over secant x plus tangent x dx. So you add just in a 1, and so that's fine to do because you haven't changed anything. And then you, in that integral, you basically do a u sub, and so you're going to, if you let u equal secant x plus tangent x, and then you do the u sub out, you'll actually see how you can get it, but I'm not going to go through it right now. It's kind of a classic like Calc 1 thing to show that, but that is what it equals. And then if you just go and plug in pi over 4 and 0, you'll get natural log of 1 plus root 2. In there you get like a natural log of 1, which goes away eventually and stuff, but this is what it would simplify down to if you plug in pi over 4 and 0. So that, number, all that means, right, is that if you graphed this on like Math 3D or something, and you look between, you let t range from 0 to pi over 4, then this is how long the curve is. That's all we figured out. And there's another way to technically do this, and this is something that they call the arc length function. And the arc length function is a function of t. Maybe I'm going to just kind of write that function of t. And they have these du's in here that you see. Those are what we call just like a dummy variable. It's like the u sub when you do that kind of. The reason it's a function of t is that there's a t right here. So if you do the integral out, you're going to get a t in the end based on how you evaluate that definite integral. And what this thing is doing is it's a bit of a variation on the previous one, because the other one specifically went from A to B, like here's 0 to pi over 4. But this one goes basically from like R of A, like right here, this vector, up to some like R of t vector. So you can kind of treat it as a function of time, and you're like, maybe this is time equals 1, time equals 2, time equals 3. Out here is time equals 7 or something. But basically you can move along this curve, and you kind of get new vectors based on whatever time you are. So it's a way to get a function of time, and then you can evaluate all this and then just plug in numbers like 1, 2, 3, or 4, and you'll get like how long, I should say, the arc is up to that point. And this is something that's kind of unrelated right now, but I wanted to show it. So we're going to study something, these curvature formulas in a second here, and there's 2 of them. And not today, but next video, I'm going to actually show why those 2 formulas are the same. And an important part of that is going to be understanding why ds dt is equal to the magnitude of r prime. So it's not too hard to see. Basically, if you just take ds dt of both sides here, so you just take, d dt of both sides, then you get from this that ds dt equals, what happens here is that d dt of this integral just gets killed, and then this stuff this also gets killed. That's what's going to be right here. And what that is really just the magnitude of r prime. Just the magnitude of r prime. So this is just going to be an important result that you'll see kind of being used later on. But if I have this, it makes sense to show this right now. So if you just take d dt of both sides, you can kill that integral, and you could just see that ds dt is the magnitude of r prime. All right, so curvature. Curvature is basically a measure of how curvy something is. So there's technically 2 ways that we compute curvature, and they use K for curvature for some reason. And there's a whole bunch of things in math where you could really dive into this. There's a whole area of math called, if you want to Google it, it's called differential geometry. And I took independent study with this class in undergrad, and the differential geometry uses a ton of curvature kind of work. And so there's also something called there's tons here, but there's also something called the TNB frame. And the TNB frame is actually in your book, and this has to kind of do with curvature and differential geometry, but it's a whole nother area of math that would take forever to talk about. But a lot of engineers use this, a lot of physicists use this. If you're ever creating something in 3D, I would imagine even graphics design works use this kind of stuff. But I just want to show you kind of how these formulas work. That's the plan. So we haven't really used it too much, but we have seen this capital T prime of t. That is the unit tangent vector. And that again just means it's r prime of t over the magnitude of that vector r prime of t. And so basically it's a length 1 r prime of t vector. And so if you just do the magnitude of capital T unit tangent vector of t over r prime, that measures curvature. And there's another formula where you can do r prime cross r double prime, and the magnitude of that over the magnitude of r prime cubed is another way to compute curvature. And this is a cool little picture video, but I screenshotted this to make these videos here, so it's not going to work, but I'll show this to you in class sometime. But it basically shows you, as you move along this curve, what the curvature would be. So like one part that I can tell you specifically, as you move along, so in the video they're moving this way, and those are arrows, but right here, and also right here, those are two spots where actually there's like zero curvature. So the red one is going to correlate to there roughly, and that first like purple vector would be here. And actually if you do the whole thing out, if you do this out, the map of the curvature, like the graph of it, looks something kind of like that. But I'll show you the video, which I think makes a lot more sense when you see it moving around. But it literally measures like how curvy something is. So like just as an intuition kind of problem like this, larger circles, right, versus small circles, this one would have less curvature. And this one would have more. It literally measures like, you know, how fast you have to turn to go around it. And this one, you don't have to turn as hard, right? Whereas this one, it's like turns really quickly. And this actually becomes an important characteristic of like space curves, like these vector valued functions. These two formulas really do the same thing, but we really use this one if we're given like a 2D space curve. And this one is only used for 3D. And the reason we use it for 3D is because of the cross product. So the cross product is a 3D vector computation. We have that like ijk component to it. And it doesn't work well in other dimensions except 7, but that's like a whole nother story. So we can use either, but if we're in 3D, you'll see that I typically use this, and if we're in 2D, we use that one. So I just wanted to do an example of one of these. So just finding the curvature of this vector valued function, and we're going to use the kind of 3D version because we have 3 components. And then just to show you how you can, because this is going to be a function of time, we can plug in t = 0 and get the actual like measurement of that curvature at time 0. So basically what I do is I just start building this thing up. So I find r prime, which for this would be 1, 2t, and then e to the t. R double prime would be 0, 2, and e to the t. Oops. And then we're going to need a cross product. So we got I, j, k. We got 1. Wait a second. Yeah. We got 1, 2t, e to the t. I looked at the wrong thing for a second. So, then we got 0, 2, and e to the t. And if you do that out, you would get 2t e to the t minus 2e to the t in the I component, and then you get e to the t in j, and 2 in the k. You can literally plug these into like a TI Inspire or something. It really will do cross products with variables. And then like at this point, I don't mind if you do that on your TI Inspire. You should also be able to do it by hand, but everyone does them on a computer or calculator once you get to like this point. So then you need to do the magnitudes of these vectors. So it's kind of a lot of computation, but the magnitude of r prime, I'm just trying to think of where to put this. Magnitude of r prime is the square root of 1 plus 4t squared plus e to the 2t. And then the magnitude of the r prime cross r double prime is the square root of 2e to the t times t minus 1 all of that squared, and then plus e to the 2t plus 4. So the curvature is literally just that big messy thing, 2e to the t times t minus 1, all of that squared, plus e to the 2t plus 4, over the square root of 1 plus 4t squared, plus e to the 2t, all of that thing cubed. Okay? And, this is just some big messy thing, but if you go and you plug in 0, it actually works out fairly nice. If you go and evaluate this thing at 0, you're going to get k of 0 is 3 over 2 root 2. And, this is kind of a unitless number, but it's more about like a comparison. Like to have, curvature maybe 0 be greater than curvature at 1, that's like more what we're kind of curious about. And so, and then there's also the notion of like negative curvature or positive curvature, and that's kind of also relates to, it does relate to the direction it's turning. But these are the kind of things that you can really like dive into more in like a differential geometry class or something. But really, most of the time for us, it's just, I'm going to be asking you things like, it doesn't have greater curvature at this point or something like that. And basically you'd have to compute the curvature, like the k of t, and then you have to plug in the numbers and like compare them.